Okay, students, we will start with the stoichiometry of chemical reactions. Substances which react are known as reactants, and the substances which are formed after the chemical reactions are known as products. We all know about this. Now, in the chemical reaction, what I have shown to you is nitrogen reacting with hydrogen to give us ammonia. And nitrogen and hydrogen on the left hand side are reactants, and ammonia on the right hand side are the products. Now, it requires a quantitative study of the reactants and the products. How much of the reactants you have to take and how much of the products you need, that depends on your requirement, particularly on your requirement. And it's very important for us also, so as to not waste much of the reactants and to obtain the maximum amount of the products. For example, in case of medicine, suppose in the analytical chemistry, we find the makings of medicines as a very important ones. So in case of medicine, if any of the ingredient is in excess quantity, it may harm to us or it may have very adverse effects on us. So for that reason, we have to be very particular with the amount of the reactants what we are taking compared with the amount of the products. So in this cases of stoichiometry of chemical reactions, first thing we have to do is we have to take a balanced chemical reaction. The chemical reaction must be balanced in the first step. Then from that we will obtain many such informations which I am going into that. Before that, we will just give a definition of stoichiometry. Stoichiometry refers to the quantitative study of the reactants and the products involved in a chemical reaction. Now, the stoichiometry word is from the Greek word stoichein, meaning element, and metron, meaning measure. And this was first coined by Jeremias Richter. Now we see the balanced chemical reaction. As I have written, N2 plus 3H2 gives us 2NH3. Now how is it balanced? We already know this. There are the number of atoms of different elements on left hand side and the right hand side would be same, as you can see here. You have 2 nitrogen atoms on the left hand side as well as 2 nitrogen atoms on the right hand side, and in this way. So first thing we have to know is the balanced reactions, that the stoichiometric coefficients gives us many informations. It gives us a ratio, and from that ratio we can find many informations. So here there is no coefficient, means it's 1. So 1 before nitrogen, 3 before hydrogen, and 2 before ammonia. So in terms of that, we first derive the smaller concept, that is molecule, and then we later go for a bigger concept, that is mole. In terms of molecule, 1 molecule of nitrogen is reacting with 3 molecules of hydrogen to give us 2 molecules of ammonia. And if that is taken as a large amount, because in chemistry we deal with a large number of molecules, we don't deal with 1 or 2 or a very small number. So in case of that, you suppose you require 2 into Avogadro number, that is 6.022 into 10 to the power 23 molecules you require of ammonia. So how much of nitrogen you are going to take? Na, that is Avogadro number of molecules, and for hydrogen it is 3 into Avogadro number of molecules. Now from this, in the terms of mole, how can we derive to the number of moles? See, Avogadro number, that is 6.022 into 10 to the power 23, we know that that's equals to 1 mole. So from that concept, it is 1 mole of nitrogen reacting with 3 mole of hydrogen to give us 2 mole of ammonia. Now we go for terms in the terms of mass, which is very important here. In terms of mass, we already know that 1 mole equals to the atomic weight, atomic mass, or the molecular mass, as and when required. Now it's nitrogen molecule, so it is molecular mass of nitrogen we are taking here. And for hydrogen we are taking 6 grams. 6 grams because 1 of that molecule will be 2 grams and you have 3 of them. Okay, 3 mole you have, so it is 6 grams. 1 mole of ammonia would be 17 grams and you have 2 moles, that's why it is 34 gram. Now, as these are in the gaseous state, all of the reactants and the products in the ratio of 1:3:2, which is not going to change anyhow. Now, in terms of volume, you can write that 1 mole always occupies 22.4 liter. That is the molar volume we know. So that is 22.4 liter of nitrogen is reacting with 3 into 22.4 liter of hydrogen. That is 67.2 liter of hydrogen to give us 2 into 22.4 liter of ammonia. That is 44.8 liter of ammonia. Now, suppose it's told to you that you required 22.4 liter of ammonia only for a reaction, and you don't know how much of nitrogen you require, suppose. So, first thing we have to do is, from the balanced reaction, you have to write that yes, my 2 into 22.4 liter of ammonia is coming from how much of nitrogen from the reaction? We can see 22.4 liter of nitrogen. It is coming from 22.4 liter of nitrogen. Now 1 liter would be coming from, it's just a unitary method. You divide it, 22.4 divided by 2 into 22.4. And what did I tell you? You require only 22.4 liter of ammonia. So you require 22.4 liter of ammonia, and how much of nitrogen you want to find out. So how do you do it? 22.4 divided by 2 into 22.4 as told, unitary method, multiplied by 22.4. You require it, right? So you just cancel it, and what do you get? 11.2 liter of nitrogen you have. Okay, that's very simple. Next, go for some other problems. We have this problem, numerical problems, where weight to weight relationship is given in terms of mass, what I have discussed now. So this reaction is very simple. C plus O2 gives us CO2. Okay. Now C plus O2 gives us CO2, which directly means that it's 12 gram. Okay, 12 gram of carbon, because it's an atom, an atomic state. 12 gram of carbon reacts with 32 gram of oxygen to give us 44 gram of carbon dioxide. So that's what it is given to us. Now, they asked me that 33 gram of carbon dioxide is obtained from how much of carbon? So I know that from the balanced reaction, 44 gram of this CO2 is obtained from 12 gram of carbon. This is from my balanced reaction only. This information is from balanced reaction. So 33 gram we will obtain from how much? Unitary method. It's 12 divided by 44 into 33. That much gram of carbon I will require. Okay. Now a little bit more we go for the details of this weight-weight relationships only. Here it is told in the next problem that 200 gram of mercuric oxide, when heated, it will give us oxygen. So first we have to write the reaction. Okay. First let us write the reaction then. Here you can do it with two different methods. I will just show you my method. You can do in the terms of moles as well, gram moles also. Now what we are going to do is AgO. This is mercuric oxide. Now this gives us Ag plus O2. Okay. This is giving my Ag plus O2, and I have to balance it. I'll just balance it. This is how I have balanced it. Okay. Now, this gives out oxygen as it is told in the reaction. The question: find out the amount of KClO3 which needs to be heated to obtain the same amount of oxygen. Now let us find from the reaction, first reaction, that how much of oxygen is actually given. That much of oxygen we need from KClO3 also. So we have to find that KClO3's amount. Okay. First start with this reaction and just find out. See, Ag you will have the atomic weight as 200.5. So here ultimately you get 2 into 216.5 actually. Okay, 216.5. So this much you are getting when decomposed, this much of mercuric oxide, when decomposed, you are getting 32 grams of oxygen, isn't it? As from the balanced chemical equation we can get. Now, they have told us from 200 grams. So 200 gram of mercuric oxide when decomposed will give us how much of oxygen? 32 divided by 2 into 216.5 multiplied by 200 grams. Okay. So that much will be given. So that much oxygen we require from KClO3. Now, first of all, write the second equation as KClO3. KClO3 gives us KCl and oxygen. Now balance it. It's 2 KCl, O3, 2 KCl and 3 O2. This is how it is balanced. Now from the balanced reaction, what we are getting? How much of oxygen is derived from how much of KClO3? We can see that 3 into 32 gram. 3 into 32 gram of oxygen, we are getting it from how much of KClO3? You just find out K 39 and Cl 35.5 and plus 48, and you do that like that, and you will be finding that it's 122.5. And as we have two molecules here, 2 moles here, so you have to write it as 2 into 122.5. That's the molecular weight we have found out. Okay, so that much of oxygen is giving us this, and we require it from this. Okay, so you can cut it off 16. So 16 by 216.5 multiplied by 200 of that oxygen will be obtained from 2 into 122.5 divided by 3 into 32 unitary method. If you find it from worth 1 gram of oxygen will be derived, then it gets divided, multiplied by this number you have to take here, and you calculate and you can arrive at the result. Okay, you can just do it afterwards. If you have understood, you can just do it afterwards. Let's start with the next one, next numerical. Now you see, the next numerical is with weight volume calculation. What is given to us? A balloon of 1000 liter needs to be filled with hydrogen gas. Temperature and pressure is 30 degrees centigrade and 750 millimeter pressure. How much of iron is needed for the production of the required hydrogen gas? Now, the thing is that when it is a balloon of 1000 liter, you just assume that yes, 1000 liter of hydrogen gas you require. This you have to assume. And from this, whenever the gaseous elements or the molecules will be given at different conditions of temperature and pressure, you have to first find it out at STP conditions, and then you can go for from the balanced reaction, because from the balanced reaction whatever we are estimating it as at STP. Okay, the first thing we have to go in that way, and for that we get a method as P1 V1 by T1 equals to P2 V2 by T2. Okay, so that what we get is P1 V1, you just put P1 as 750. Okay, if there is requirement, I'll just put it, okay, 750 as it is given here, 750. Volume is given as 1000 because we require it in 1000 divided by T1, that is T1, it's given as 30 degrees centigrade. You convert it into Kelvin always. Okay, so you get it as 273 plus 30 here. Okay, now equals to P2 V2 by T2, that is 760 pressure always. We don't know the volume, we just take it at X, divided by T2, that is always 273 at STP conditions. Okay, now what you get is your volume equals to comes as 889.13 liter. 889.13 liter. Okay, now that much of volume of hydrogen gas, you have to get it from iron. Now how much of iron you require to get that? So first thing is iron gives us hydrogen gas. Now how? Hydrogen reacts with iron, reacts with water. to give us the iron oxide Fe3O4 plus hydrogen. And then we have to just balance it off. You have just balanced it, just see, 3Fe plus 4H2O, Fe3O4 plus 3H2. Okay, sorry, 4H2. That's 4. Okay, 4H2. Now from the balanced equation, what you are getting, that you have to find out. See, this is in liter. Okay, hydrogen is in liter. I'll write it in liter, and iron is a solid, so I'll write it in grams. So from the reaction, what we are getting is, see, 4 into 22.4 here you'll get, and it's coming from 3 into Fe. For the Fe's atomic weight is 55.8. So I can just say that 4 into 22.4 liter of hydrogen is obtained from 3 into 55.8 gram of iron. So I'll just write that 4 into 22.4 liter of hydrogen, you get it from 3 into 55.8 grams of iron. Okay. Now, you require how much? You require 889.13. That 1000 liter is actually 889.13 at STP. Okay. So you find it from unitary method. When you write 1, you just divide it, right? So I'm just not doing that step. I'm just going for the last step, that is 89.13 liter of hydrogen will be obtained from 3 into 55.6 divided by 4 into 22.4 into 889.13, and the result comes as 1662.65. There's no space over here, I'm just writing it here, 1662.52 grams. So 1662.52 grams of iron is required for the production of the required gas, hydrogen gas. So that's how you do the problems. You can just ask me if you have any doubt with these two questions, three questions which I have given to you, and I am also giving you to solve it. If needed, I will tell you again. Okay.